Kamalika, are you there? Can you hear me? Can you tell me?
Hello, can you
Yeah,
hear me?
I can hear you. Can you hear me?
Yeah.
Okay, so we'll get started. See, the whole thing was running a little late, so the two parallel tracks are were slightly out of sync, and therefore there's a break right now, and hopefully people will come and join, but we'll get the talk started anyway because otherwise it'll get very late. And this will be recorded so people can view it online, even if they're not here in person right now. Okay, we have some people here in person, and hopefully more will join soon. Is that okay?
Okay.
Okay. Yeah. So can you share your screen?
Yeah, sure. Can you see my screen?
Yes, we can see your screen. Can you make it full screen?
Yeah.
Yeah.
Now can you?
Okay. So welcome to the last session of RHPL. We have Kamalika who will talk about logical model of cellular automata. Kamalika, over to you.
Thank you. This is Kamalika from NIT Trichy. I'll be talking about logical model of cellular automata. This work is jointly done by me, Professor Shukanto Das, and Professor Mihir Kumar Chakraborty, and it's published in the Complex Systems. So the objective is development of a system of formal logic where cellular automata, basically one-dimensional cellular automata, will be a model. So we know that logic is nothing but a pair, L and turnstile, where L is the set of sentences called languages. The members of the L are the well-formed formulas, and turnstile is the consequence relation. So how we get the L? L, we need an alphabet and a set of formation rules. And this turnstile we can define in several ways. One way is the natural deduction, where we only use a set of rules but no axioms to reach to a conclusion. In this case, we are going to do the same thing. We are using natural deduction to define the consequence relation, and we name our logic as the LCA. The syntax is, first we need a set of symbols. Our set of symbols is denoted by P, where P has some propositional constant, P0 to Pd minus 1, the number of propositional constant, and rest are the propositional variables. So our alphabet is the symbols of P along with sigma, star, and the brackets, opening and closing bracket. We start the atomic well-formed formula as the all propositional constants and variables. Then we define the formation rules as the all atomic well-formed formulas are the well-formed formula. If alpha is a well-formed formula, we take bracket alpha and sigma bracket alpha as the other two well-formed formulas. And if alpha and beta are two well-formed formulas given, then alpha star beta and alpha beta are well-formed formulas. These are all that can be included in the formation rules. Let's take an example. Suppose we have P as P0 and P1. Then our non-atomic well-formed formulas can be bracket P0, sigma P0, P0 P1, P0 star P1, sigma sigma P0, and so on. We take two spatial kind of forms. One is sigma to the power k alpha, where sigma is applied k times, and alpha to the power k means alpha is taken k times. We define normal form if the well-formed formula is in this format, like sigma to the power k1, p1 dash star, sigma to the power k2, p2 dash, this way. So in that case, the formula is named as in the normal form. We use two classes of rules, some spatial rules and some temporal rules. The spatial rules are, there are 5 such spatial rules. And we also take an equivalence relation R over this L. And we define the derivation if alpha, we call alpha turnstile beta if and only if there is a sequence where alpha 1 is alpha, alpha 2 to alpha k, where alpha k is beta, and alpha I is obtained exactly from alpha I1 by application of the rules of the logic. So only alpha I minus 1 we are considering for taking the next step. So our spatial rules looks like this. There are some introduction rules where this introduction rules means we are introducing new symbols into the formula. These are the introduction rules, and some elimination rules where we are removing something from the formula. And our temporal rules are where we are replacing one formula by another formula. So there are n temporal rules where n is the size of the p, the propositional variables and constants. This is an example of a derivation. So if we have starting from alpha, we can just apply our rules and finally we can get beta. This temporal rules, you can see we are using some temporal rules as well as the spatial rules. Now we say a derivation is in standard form if this sequence is follows. First, we use the introduction rules, then obtain the normal form, then use the temporal rules, and finally use the elimination rules. So obviously, this particular derivation that I'm showing is not in the standard form because here we are using temporal rules before getting the normal form itself. Now we can go into the semantics. In the semantics, we give the interpretation. So first, we give the semantics in the domain D, where D is the set of all D array strings. D is taken as greater or equals to 2. We say that the sigma is interpreted as a unary operator and star is a binary operator. And this W, that set that we needed for some of our spatial rules, this is a arbitrary but non-empty set of strings. We define this sigma like this. Sigma is a shift operator. So if we have a string and we take this string, suppose this string is a well-formed formula. Now, if we apply sigma over this, sigma to the power k of b, where b is this string b0 to bl minus 1, this is nothing but k times left shift of the string values, and we start with bi in that case. So k is related to I as k is equivalent to I mod L. So for example, if we take sigma of this string 0, 1, 2 to 1, sigma here applied only once. So it is 1, 2 to 1, 0. Similarly, sigma q 0, 1, 2 to 1 will be 2, 1, 0, 1, 2. Our binary relation that we have taken in the syntax, now it is defined like this. Suppose we have two strings A and B. So R of AB holds if and only if the R prefixes and L suffixes of these two strings are equal. Take an example. If we have two strings like 0, 1, 2 to 1 and 0, 1, 1, 1. Now, if we take R and L equals to 1, we can see that for the first string, R equals to 1 means the string is 0 and 1. And in the next case also, the same thing, 0 and 1 we are getting. So they are related. However, this R of 0, 0 and 0, 0, 1, 1, that doesn't hold. So this relation we can show that it is an equivalence relation. It will be going to be reflexive, symmetric, and transitive. And now using this relation, we define our binary operator. So our binary operator is defined over two strings when this, say our two strings are A and B. So R of AB, if it holds, then A star B we can write as the concatenation of these two strings. So star is a partial operator. It holds only if R of AB holds. Examples, again the previous string 0, 1, 2 to 1, 0, 1, 1, 1. This we have already seen it. If these two strings are related, so we can write 0, 1, 2 to 1 star 0, 1, 1 as the string concatenation of these two. So our semantic domain is now D sigma star. Interpretation is given in the semantic domain using a valuation function. Our atomic well-formed formulas have to satisfy these three conditions. Basically, it is 4 conditions. So this two atomic formulas valuation should not be same. Though if one atomic formula and another atomic formula's shift equivalent has same valuation, that cannot be a valid case. Similarly, we cannot write V of P as equals to B of P dash star B of P double dash. These are the conditions for atomic well-form formula. So, for example, if we take valuation, suppose we have in P, we have four propositional atomic formulas, propositional constants and variables. So we cannot give this as valuation as 0, 0, 1, 0, 0, 1, 0, 1, 0. Because this 0, 1, 0 is nothing but shift of 0, 0, 1. Similarly, 0, 0, 0, 0, 1, 0, 0, 1. This also cannot work because 0, 0, this is nothing but 0 star 0. But if we give it as 0, 0, 1, 0, 0, 1, 0, 1, 1, or suppose 0, 0, 1, 1, 0, 1, 1, this can be a valid valuation. For non-atomic well-form formula, we use this definition to give the valuations. Similarly, suppose we have, we take an example like alpha is given as this, V of sigma of P1 star P2, sigma of P3 star P4, and we have the valuation of the individual component, then we can find V alpha like this. So this is how we work. Yes.
Yeah. So is there some way in which you know whether there exists a valuation or not, or is there some way to check that?
We have to see this, whether this condition is satisfying or not. Where is it? This atomic formulas, whether it is satisfying or not.
Okay. Also for the second one, do you need P and P prime to be distinct?
Yes. P and P prime need to be distinct. P and P prime has to be distinct in the case of sigma invariant also.
Okay, sure. Yeah, you have about 4 minutes.
Okay, I'll go quickly. Yeah. So now we can also give the interpretation of our rules. I'm not going into how we are interpreting. So suppose these are the temporal rules interpretation. So we can give the temporal rules here. You can see that at step 1, 2, 3, 4, 5, 6, around 10, we are giving the temporal rules, and accordingly we can find the derivation. So this is a theorem that we can prove that V alpha is going to be reducible to V beta, where V beta will be in a normal form. So this is an example. So for every semantic derivation in D, there exists an equivalent semantic derivation in the standard form. So for here, we may not be following the standard form, but this can be done using the standard form as well. This we can show. Now we go into the cellular automata as the model of this logic. So model is nothing but an interpretation. How here we define that a derivation is called an evolution if the derivation uses at least one temporal rule. For one cellular automata, if we maybe knowing this, that it is nothing but a discrete dynamical system which evolves. So for cellular automata, we need to show that here that the dynamics of the CA can be represented by as a derivation of this logic. So I'll not go into the details of how CA is represented. This CA is any kind of CA can be represented by a de Bruijn graph also. And this de Bruijn graph is instrumental here to map the CA as the model of the logic. So what we do, we take the de Bruijn graph representation of the CA. Here, elementary cycles of the de Bruijn graph, these are basically our atomic well-form formulas. And the next state values of these elementary cycles, which we can get just by the levels of the de Bruijn graph, those will be taken as the strings that is replacing the temporal sequences. So I'll go into an example, it will be more clear. Here we have, in case of cellular automata, we have two types of lattice. One is infinite and another is finite. In case of finite, we have periodic boundary and open boundary. Periodic boundary means it is kind of like a ring, and null boundary, which is an example of open boundary where we are just terminating the cells, and at the terminating cell, there are some fixed values. And we can show that both the cases can be models of the logic. Similarly, infinite lattice also can be shown that where the lattice is infinite, there are no boundaries, they can also be shown as a model of this logic. For infinite lattice, we need a quiescent state, where quiescent state means this particular state is not changing. It is irrespective of the update, it remains as it is. So first, the periodic boundary here directly this is the interpretation. So propositional constants are the states, propositional variables are the elementary circuits, and if this sigma k alpha, that is nothing but shift equivalent of the homogeneous configuration and so on. So here I show an example. This is rule 90, a very famous rule, which is an ECA, elementary ECA. Here you can see that these temporal rules we have derived from the elementary cycles of the diffusion graph. So here first elementary cycle is this 0, 0 over 0, 0. So this is 0. And the next state is 0. So this first temporal rule is 0 by 0. Similarly, 1 by 0 and so on. Now, if our initial configuration is the first string, just by applying these rules, we can get the last string, which is the next configuration derived from this initial configuration. Another example, this is for 3 state. Here also, we are taking the
wind up soon.
Yeah, sure. So here also we can show that we can represent the evolution of the CA by using the temporal rules and the spatial rules of the logic. So similarly, open boundary also we can show an infinite CA also. Interesting thing is in our logic, we are not restricted. We are just saying that an evolution needs to use one temporal rule. But if you see the previous cases of the evolutions of CA where it is synchronous, so all temporal rules were applied together. Here you can see at this last, I don't know whether my cursor is visible or not. Here we can see that all the temporal rules are applied together, but this is not the restriction of the logic. So just from the logic, we can actually get a new kind of CA, where we name it as homoasynchronous CA. It is a kind of asynchronous CA, where the block of cells which are part of the same homogeneous configuration, they can be updated together. So this is a new class of CA that we get as an outcome of this logic, which was not already existing in the CA. And its evolution is completely different than the synchronous CA and the fully asynchronous CA. So this is an interesting result that you can get out of the logic. And obviously, there will be many more possibilities to see. And shift equivalence, which classically doesn't hold for periodic configuration, this also we can see that it is holding for this in case of the logic for open boundary condition. And maybe it can be extended to other dimension as well. This we have not explored, but we believe it can be done. So thank you. If you have any questions, I'll be happy to answer.
Yeah, thanks, Kamalika. We may have time for one quick question. Okay, yeah. So I wanted to know. So you talked about the derivation, and then you said that there is this proof rules that you have where you don't use assumptions, you don't use axioms, but you just use rules, and then you have this semantic derivation. Is there some connection between the two, or
we don't need axioms here actually. So from the syntax we did the syntax we have derived, then from there we get the semantic derivation, and from the semantic derivation we had the background as the de Bruijn graph. So anything that is using the de Bruijn graph, that can be actually modeled by this logic. So you can see actually this atomic well-formed formulas. These are nothing but the cycles, elementary cycles of the de Bruijn graph. So our evaluation is given in that way.
Okay, sure. Yeah. Thanks a lot, Kamalika. We can, we'll have to wind up now. But yeah, thanks for your talk.
Thank you.
So we now have the last talk of this session. Jyoti will be giving this talk. Jyoti, can you share your slides?
Yeah, skip. So are my slides visible?
No.
Okay. Now?
Yeah, now we can see it. Okay. So Jyoti will tell us about demand-driven information flow analysis. Yeah, Jyoti, over to you.
Okay, so today I'm going to talk about demand-driven information flow analysis of Android WebView apps. And this paper is presented at ISRE last year at Florence. And I'm Jyoti Prakash, and I'm presenting this paper. And this is with my co-author Abhishek Tiwari and Christian Hammer. So Christian Hammer was this work was done during my PhD when I was doing PhD with Professor Hammer. Okay. So yeah, since I'm working in a commercial organization, so a disclaimer that what I'm presenting here are my own opinions and that does not reflect the policies or positions of my employer or any affiliated organizations. Okay, so now coming back to the topic, like what we have in this hybrid apps is that so hybrid app is a system in Android which allows you to use web technologies to develop Android app. So if you have used any such social media applications such as maybe LinkedIn or Facebook or anything, then you might have seen that if you click on some say some advertisement or some page on some link on that, then it opens a browser. So this browser, so this browser is something which is called an embedded browser which is runs within this Android app, and the app that combines this browser thing with the native Android is called as an hybrid app. So in hybrid app, there are two components. One is Java and Kotlin, which is the Android component, which is written in Java and Kotlin, which is being compiled to text files. And there's a web component, which is written in web technologies, what I mean, like HTML, CSS, or JavaScript, or and whatever is there. And this runs within an embedded browser within this Android app. And the way to execute is that this two runs in two different threads. So that means there are some synchronization issues which happens, which will show that how it affects the data flow analysis, and that we have done one of the part that we've done in this paper. And the flex and why I'm interested in this problem is that hybrid has become like has gone famous, that is many popular apps use it, and since it allows the developers to reuse an existing web portal directly into and build and repackage that web portal as an app. So that's why this is quite convenient to developers, and they have been using it and the use of this hybrid app has been is completely increasing. So now come back. So now what happens in this hybrid apps is that what I talked about is that we have two components. One is the Java, one is the Android, the web component, and the second is the native Android component. So as I said, the native Android component is written in Java and Kotlin, and the web component is written in any web language. And this runs the native component is called as a host language, and this web component is called a guest language. And we invoke the guest language, that means the web component from Android apps. And on top of that, it is also possible for for a developer to basically call uh, uh, host language, call a JavaScript code from the host language, and also access some part of the Java code in the guest language. So, and this thing happens by the means of this shared variables and the shared methods, which I'll talk in the later slide that how it's being achieved in the Android ecosystem. So now let's to basically concretize this idea. We'll concretize this idea that how the web component interacts with the native Android component. We have something called as a web view, which is a class defined in the Android standard library. And then we have some APIs which allows you to communicate with the web component. For example, here we have one API called as evaluate JavaScript, which, as the name indicates, it basically it can call any JavaScript method defined there. And then we have something, and then there's another API which is called as load URL, which allows you to load any URL, maybe any public website or any such file, HTML file which is packaged with the app. And also there's a special thing provision in this with this API with load URL that one can allow to execute Java code with JavaScript code, sorry, by simply prepending a fake protocol called JavaScript with the JavaScript code. So this will basically give a signal to this will message the runtime to call this JavaScript interpreter at that particular location. So and now coming to after this APIs, there are certain set of methods which are basically shared from the Java part to the JavaScript part. And the way a developer can enable this thing is to annotate the methods, the method with @JavaScript interface. And with this, basically the Android runtime knows that this method can also be called by the JavaScript, and it is available to the shared memory. And now coming to the JavaScript part, the way we access Java methods, such as this bridge methods, which is in this case set value from the JavaScript part, is through alias object, which in this case we named it as JS object. So first at line number 2, we create an object of this, an instance of this of the class, and then we given alias to this instance, and this alias is accessible from the JavaScript part. So using this alias, the developer can basically use any such Java method and call it from JavaScript. So this is how the multilingual programming in Android looks like. Now, what is the problems with such an environment is that it increases the attack surface area, and we'll see what are the problems that happen with this. So we have this Android hybrid app, which is our trusted component. And when we expose the Java part through an web through the JavaScript part, which can interact with the web, maybe suppose it calls an external API and uses it results. So this can basically this can induce the control flow, influence the control flow, and also pass some data, which is quite expected, and we don't know, and sometimes we don't know the source of this data. So this we call that as an integrity violation, when an external untrusted data can basically break the sanity of the trusted component, which in the case is Android. We assume that Android is trusted because it runs within the sandbox, and it has this permission system encoded enabled with it. And then there can be a dual confidential leak where an internal Android value can be leaked through this bridge method to an external untrusted sync. So this we call as a confidential evaluation. And the work that we are doing is basically coming up with a static analysis to detect this integrity and confidential evaluations in Android hybrid apps. Now, what are the peculiarities of communication that happens because of the asynchronous nature of this Android and web components? So in this program, we have something called as we add JavaScript interface, and in line number 2, we defined a public data which is stored in a field called as G, and then at line number 3, it calls the load URL function, which basically enables the web communication and calls the JavaScript method read. And after this statement, it modifies this field G. So naturally, the expected behavior is that G should contain public data. So at line number 3, when there's a leak of X, then it should naturally leak the public data. But this is not the case. Because of asynchronous nature, the Android part waits till this function is executed. So it will fetch instead of having public data, it will fetch the value secret to the bridge method get G. Are there any questions?
No, Jyoti, there are no questions. You have about 12 minutes left.
Okay, yeah, I'll try to wrap up quick. And then we have something, and then the second thing is since this is JavaScript and it is, and one can basically manipulate, basically override this IFC object which is possible in JavaScript, and add a function, get G function here, which does something other than returning the field G of from the Java part. So this works as expected. It overrides this IFC object, and so an IFC object.get G will return the localized IFC object the variable rather than the alias IFC object from the Android part. And in this last case, when we have what happens if we can delete this IFC object, which is also possible in JavaScript to delete a variable. And in this case, the Android runtime will basically ignore the delete operation, but which is expected that it should delete the bridge object. But in this case, it will simply ignore the bridge operation. So these are some of the peculiarities that can happen in WebView and WebView communication. And we defined a tool called as a technique called as IVAndroid, which does an information flow analysis. And this runs in a demand-driven fashion that it doesn't compile the it doesn't analyze the whole code, but it analyzes a part of the bridge method code. So in the first step, it extracts the bridge method details. So it takes the APK file as an input and extracts the bridge information and the methods which invoke this bridge communication, like load URL and evaluate JavaScript, and also does some string processing to extract the JavaScript. Since the JavaScript code in this part is represented as a string, so it simply does some string processing to static string processing to extract the JavaScript code. And finally, it does an information flow analysis, which runs in 3 phases. In the first phase, it analyzes the bridge methods and it collects some summary information, which is then propagated to the second phase. In the second phase, it analyzes the information flow analysis of the invoking methods. That means those methods in the Java part which are involved in which uses load URL and evaluate JavaScript APIs. And in the third phase, it takes the summary information from the 2 phases, and then analyzes the JavaScript to compute the information and confidential devolution. And all of this thing has been encoded in the IFDS and IDE analysis framework, which is something that I'll briefly explain in the next part. So what's an IFDS and IDE analysis? So for those if you're not aware of this thing, but many of you might already be aware. So this is a data flow analysis which solves. So this is a data flow analysis framework which solves it using graph reachability. So assume that we have this program here where P is equal to public and then S is secret. Then we do some assignment with L is equal to S, P is equal to L, and then leak P. And we want to determine whether this value secret is secret. Obviously, from the look of the program, it looks that this is being leaked, but we want to see how we can compute it automatically. So in the first phase, we take the S as the set of solutions. Then we add in the transfer function is that we add P to the solution. And in the second transfer function, we say that we add S to the solution. And then in the third phase, we add L to the solution if S is already there in the solution. And the fourth transfer function, we add P to the solution if L is already there in the solution. And the way it will compute is with simple graph reachability, that we take a data flow facts as nodes and we number it from 0 and we label these nodes as 0, P, L, and S. And then we compute this transfer function with something called as a bipartite graph. But I'll not go into details of it. It's just give you an overview of how we're computing it. So in the first phase, it will add P to the solution. Then in the next phase, it will add S to the solution. Then since S is already there in the solution, it will add L to the solution. And finally, we know that since L is also reachable from 0, so we can know that P is, then it can also P to the solution. We know that P is also reachable. And now, since now we have discovered the graph reachability, now we want to compute the information flow labels. That means to determine whether this information is confidential or not confidential. So we label this with function with encoding with environment transformers, which is in this case L and H, and then we propagate. Then we compute the environment transformers across the reachable paths. So at the final phase, if you compute at the meet, we can know that P is a secret because there are two paths which come from P and from S. And there's a special name given to this thing called as a path edge, which is a transitive closure of these edges. And with this path edge, what the big thing is that we can compute summary information. So rather than if you have computed this information once, we can reuse it without recomputing this graph reachabilities, and we can store this as summary path edges. So now we'll come to that how we had applied this technique to each of these phases. So in the phase one, we identify variables which are likely to influence. And for identifying these variables, we first check the methods which has the @JavaScript interface enabled. That means these methods are exposed to the web, and therefore the input parameter are likely to be influenced. So we compute the reachability here, that we start with T, and then we compute that X is reachable. And then we compute that this.secret is also reachable from T. So this is done in a forward analysis fashion to discover the set of access paths which are modified by the input parameters. And we keep it as a summary information like T2 and this.secret, and T2T is also one of the, and also T2X is one of the summary information that we have. Now in the next phase, we use the summary information from the previous part. So so what you see here is that we since we want to do demand analysis, so we start from the functions where we see that evaluate JavaScript or load URL has been used, and we replace this summary bridge method calls with the summary information. So in this case, the summary information that we get is IFC_object.secret is equal to public, and IFC_object.secret is equal to IMEI. So this is a program where we have where IMEI is equal to get IMEI, and we replace this with simple assignment. Now what happens? Now we do a backward analysis, and we start with line number 6 and we propagate towards line number 3. So in the first phase, we say that IFC_object.secret is influenced by IMEI, and in the next it goes on further, and we say that public information is also flows to IMEI IFC_object.secret. So now if you compute the ID analysis, propagate the security labels, and then we can say that IFC_object.secret holds us a value which is labeled H, which means a high information. And in the last phase, we use all of this summary information to detect confidential violations. So to detect integrity violations, we can simply take the summary from the first phase and reuse it, which will say that X is API.getResult, which you do not know the label. So it's an L information. So L value flows to an H value, which means that this is an integrity violation. And in the second phase, we compute similarly, where we say that this X value, which we know that IFC_object.secret is the get value here, and then we say that H this flows to X, and therefore then X is leaked. So the taint analysis will be able to resolve that X is leaked from the JavaScript part. So this is how the third phase goes. Now the last phase is like how we have to handle this this function where we can override this method. So the way we do is through a forward analysis. Then we do a backward data flow analysis to compute the target of IFC object, and then replace and then use that summary, or reanalyze it depending on the case. So we analyze this with like 19 micro benchmarks, and it was able to analyze 15 applications with two false positives, which has been reported as failed. four applications were not available. That means this was that means they do not contain any bridge communication which happens, and they merely enable the JavaScript interface. And now the next question is that how scalable is I1 on large applications? And to evaluate this, we took 687 apps from the F2 Play Store with the criteria that they should be relatively large apps, and they should have add the JavaScript enabled. And I1 was able to identify 136 confidentiality and 142 integrity violations in this suite of 687 apps. And we had reported some of these to developers, and we got a response that they fixed those vulnerabilities, which shows the efficacy of our approach. So to reflect on what we have achieved in this thing, that we have defined a confidential and integrated threat model for hybrid apps, and we were able to see that I1 is a scalable technique for analyzing hybrid apps without analyzing the whole program, and at the same time detecting the confidentiality and integrity violations, which do not require a whole program analysis. So with this, I'd like to end my talk, and I'll be happy to answer your questions. Thank you for your attention.
Yeah, thanks, Jyoti. I think we have time for one question. Let me see if somebody in the audience. Okay, so I have, I wanted to ask about, so you talked about scalability, but precision is also a concern, right? So if AFLS ID analysis is not very precise, then you will end up computing imprecise summaries. And
Yes.
I think that can, it will affect phase 2 of the analysis. So can you comment on that? How precise was it? And
so precision, we computed on the micro benchmarks, and it was precise. We were able to get a precision of around 98% or something, if I remember. Don't remember the exact number, but it was precise. For all the large benchmarks, we manually took some sample and tried to evaluate whether that this vulnerability that it is reported by I1 is an actual vulnerability. And we found that those are true positives for all of this, for all of the reported vulnerabilities.
okay, yeah. Okay, so if there are no further questions, let's thank Jyoti again.
Thank you.
Okay, so yeah, so that brings us to the end of RHPL and RHPL 2024. And I think, the only thing that remains is, perhaps I think it's important to put on record that the RHPL organizers would like to thank Neil Dara and her entire team for such a wonderful organization. Yeah. Okay, so that's all from here.
Thank you.